symmetry can help you a great deal in graphing. Sometimes you can reduce the work of drawing a graph to drawing just half the graph and then use symmetry to draw the other half. And a function is even if f of minus x is equal to f of x. So that means the y value associated to any x is the same as the y value associated to the minus x. The symmetry that this generates in the graph is that the graph is a reflection of itself through the y-axis. Basically, if you draw the right half of the graph and then fold your paper over at the y-axis before the ink dries, you get the other half of the graph. And the function is odd if f of minus x equals minus f of x. So this means the y value associated to minus x is the negative of the y value associated to x. This means that there's a symmetry through the origin. If you draw the right half of the graph, then reflect it in the y-axis and then reflect that part in the x-axis, you will get the other half of the graph. Let's have a look at two functions. F of x equals x squared plus 1. I'd like to check if it's an even function. So I'm asking if f of minus x equals f of x. Well, the way to check is to plug minus x in the formula and see if it gives you what you get when you plug x into the formula. So what I'm asking is minus x squared plus 1 equal to x squared plus 1? Well, of course, when I square that minus, I just get x squared. The minus goes away, and I'm really asking if x squared plus 1 equals x squared plus 1, and the answer is yes. So that means that f of x is indeed even. And you can see that this gives us a symmetry in the y-axis. If I were to draw the right-hand side of this graph, y equals x squared plus 1, and quickly fold the paper at the y-axis before the ink dries, I would get the other half of the graph here. In general, if I have a polynomial in powers of x which are all even, it's going to be an even function, and its graph will have this symmetry. If I have a polynomial in powers of x that are all odd, then I get an odd function, and that's what's happening here with g of x. G of minus x is minus x cubed minus x, which is minus x cubed plus x, which is minus g of x. So this is an odd function, and this gives us a symmetry through the origin. So this means that if I were to take the right half of the graph of this function and fold it first over the y-axis, and then take that part and fold it over the x-axis, I would get the left part of the function. Another way to think about this is if I take any point on the graph and I connect it to the origin, and then I extend that line the same distance beyond the origin, I get an opposite point on the graph. So if I do this with all of the points on the right-hand side of the graph, then I get the left-hand side of the graph. This is also a way of thinking about symmetry through the origin. We say a function is increasing on an interval from a to b, say, if the graph of the function is basically going upwards as we travel from a to b. So if you're hiking on this graph, your elevation is increasing as you go from left to right. Our definition captures this algebraically. The geometric concept is easy here, but the big question is, how do we write this down in numbers? We describe this by saying that f of x is increasing if whenever I pick any two numbers in this interval, x1 and x2, then I must have f of x1 is less than f of x2. And this captures this concept algebraically, and this is very useful for dealing with the concept later when we want to either check it or when we want to use it to prove theorems. And the opposite concept is a decreasing function. So f is decreasing on the interval from a to b if, when you're hiking, you're going downhill as you go from left to right. And again, algebraically, that translates to saying that if I pick two numbers, x1 and x2, and x1 is to the left of x2, then f of x1 is bigger than f of x2. The elevation at x1 is higher than the elevation at x2. There are two ways to check whether a function is increasing or decreasing, or even where a function is increasing and decreasing, because for the most part you'll find that functions are increasing on one interval and decreasing on another. Let's check this function f of x equals the square root of 1 minus x squared. Notice that this is the top half of the circle x squared plus y squared equals 1. If I try to solve for y here, I get y squared equals 1 minus x squared, and that means that y equals plus or minus the square root of 1 minus x squared. And that gives me two functions here. Y equals the square root of 1 minus x squared, and y equals minus the square root of 1 minus x squared. This one describes the upper half of the unit circle, and this one describes the lower half of the unit circle. The unit circle is just a circle with radius 1. So we're looking at the upper half of the unit circle here. It should be an even function because we can already see that that's symmetric around the y-axis. So let's check if f of minus x is equal to f of x. Well, the power of x is even, so that means that the minus goes away, and it's an even function. And this was obvious from the graph, but that means that it's symmetric about the y-axis. The question here is determine the intervals on which it's increasing and decreasing. So we're going to do that using the graph. And that means find the intervals on which f of x is increasing and the intervals on which it's decreasing, not the intervals on which it's doing both, because that's impossible. So this is our quest. Now, using the graph, we see that f of x is increasing on the interval, the x interval, from minus 1 to 0, and f of x is decreasing on the interval from 0 to 1. So if I'm hiking up this mountain, my elevation is increasing as the x values go from minus 1 to 0, and then it's decreasing as I come down the mountain on the other side between 0 and 1. One thing students often ask me about when I talk about this is, why do I include 0 in both intervals? If you check carefully, that isn't really contradictory, because the definition of increasing and decreasing involves a motion from x1 to x2, from one point to another in the interval. So if I look carefully at this interval and I pick any 2 points, x1 and x2, my elevation increases as I go from x1 to x2. So the concept of increasing and decreasing depends on the concept of motion or change. It doesn't really describe what happens exactly at one point, but it's describing what happens between 2 points.